Hello everyone, my name is Kyoung-Hee Kim and I am a professor of architecture at UNC Charlotte's Raven School of Architecture. I'm pleased to talk with you today about energy resilience in the built environment. Energy resilience strategies involve designing buildings that can withstand and adapt to energy disruptions while ensuring continuous operation for functionalities and user safety. This video is related to the renewable energy videos. Please refer to them if you want to learn more about renewable energy integration. This slide shows the climate-resilient design for healthcare facilities that enable continuous operation during climate disasters. We will use healthcare design as an example to discuss energy-resilient, broadly climate-resilient building design. Climate-resilient hospitals encompass many essential functionalities, including energy, food, waste, infrastructure, and so on. Energy resilience refers to how well buildings can withstand power interruptions and return to normal operation without prolonged delays. This is an increasingly important issue because of increasing severe storms, heat waves, and grid failure. In this lecture, we'll focus on energy resiliency for critical facilities like hospitals and other citizens supporting municipality buildings, explore strategies to make our built environment more energy resilient. As we reviewed in other resilience videos, strengthening energy resilience ensures essential services remain available when they are needed most. The energy resilient framework aligns with original state, reduce, adapt, and restore. Essential facilities should incorporate energy-efficient systems and prioritize reducing energy consumption from the first place. Then, when disaster strikes, they still enable continued operation of critical functions through backup powers and effective emergency management. When the utility grid comes back, the facilities should be capable of storing all other functionalities and returning to normal operations. Climate-resilient healthcare facilities focus on 4 interconnected core areas to enhance resilience. The first area is health workforce protection. Staff are well supported and protected from climate hazards, even during power outages, heat waves, flooding, drought, or air or water contaminants. The second area covers waste management systems. These must implement infection control practices so that safety is never compromised during such climate disasters. The third area addresses infrastructure support. Every device and consumable must be designed to work through extremes such as running lights, ventilation, and imaging in blackouts, and shielding drugs, labs, and patients from relentless heat. The fourth area is energy. Clean, continuous power from grid and on-site renewables, paired with efficient energy systems and backup power, keeps essential infrastructure and equipment working during electricity outages. These 4 areas prepare healthcare facilities to reduce, adapt, and restore to climate-resilient practice, fortifying resilience from its deepest systems outward. To reiterate, health workforce secure adequate numbers of skilled workforce resources with decent working conditions, empowered and informed to respond to these climatic challenges. Water, sanitation, hygiene, and healthcare waste management are running sustainable and safe during climate disasters. The facility must remain continuously running with backup power in case of power disruptions. Infrastructure allows for the safe practice of healthcare facility during climate emergencies. Healthcare leaders recognize that losing power or suffering damage during a disaster are life-threatening situations. Therefore, building climate resilience into hospitals is a top priority. Energy resilience prepares for sudden power outages and the continued operation of critical functions. On this slide, we see a table from FEMA about healthcare facilities' backup generators and their daily fuel requirements. As an example, large hospitals spend approximately 2,000 gallons of fuel daily, while nursing care facilities use several hundred gallons operating their backup generators during outages. This underscores the need for healthcare facilities to strategically back up powers to ensure the functionalities of critical operations. The bottom line is that hospitals must safeguard patients and staff during climate disasters. Energy resilience planning is essential to prevent such scenarios. Slide 8 and 9 illustrate architectural examples of climate-resilient hospital design. First, when locating a building, landscaping elements such as plantings, fence walls, and boulders help diminish storm surge before the building experiences a severe storm. To prevent flooding, ground floor and openings are set at higher levels above 100-year storm level. Critical patient programs should be located above ground floor to protect them from any flooding. Windows are manually operable in the event of systems failure. MEP systems and emergency services are located within enclosed penthouses in a protected location. Here is another example of climate-resilient hospital design. Architects and engineers will assess potential flooding or high wind risks and then design the facility to withstand those hazards. All critical utility and equipment are kept above potential flood levels to protect them from hazards that could disrupt power supply and critical equipment. Therefore, it is good practice to have essential system redundancy like electricity, air conditioning, ventilation, and hot water. Redundancy means having at least one extra backup unit for each critical system. If one fails, another is ready to keep things running. On-site renewable energy system coupled with backup power helps reduce grid supply and the use of backup power during emergencies. Reinforcing the building's structure and exterior helps withstand increased wind and earthquakes. The frame and facade will have extra strength to withstand high winds and even earthquakes. Windows should be impact resistant to protect against hurricanes and strong winds. Water resilience can maintain a safe water supply during climate disasters. The facility should have an on-site wastewater treatment system and backup power for pumps, so patients and staff always have access to clean water. Also, a stormwater management system across the building level, site level, and street levels will prevent the hospital grounds from flooding during heavy rains. Using less power during emergencies is an important strategy to achieve energy-efficient operation. A facility with low energy use intensity through high-performance building enclosures and efficient systems puts less demand on backup generators. Using less power means that in a crisis, the hospital can run longer on whatever backup power lasts. All these measures, flood protection, system redundancy, renewable energy readiness, structural strength, water preparedness, and high efficiency greatly improve a hospital's ability to remain operational during extreme weather events. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Thanks for your interest in resilient built environments.